online, Twitter's online, LinkedIn is online, and YouTube is online, and I have a Clubhouse over here. This is insane. You know, there was a commercial, Tim, that was Crazy Eddie's, right? Crazy Eddie's insane.
Yeah.
Furniture sale. That's right. It was furniture or appliances. I can't remember. All right. Well, guys, we are streaming. We've got. It looks like we got some people out there on YouTube watching. Chimed in. It is 4:58. We still have 2 minutes. I just want to go over, make sure everything is looking good. So I believe I'm going to just double check. Man, I'm just nervous because this is we're on 6 channels right now. So
Steve Roaming joined us.
oh yeah, there we go. Ryan
Jackson.
Jackson.
There we go.
Perfect. We got hot mics. So Steve Froming in the house, Ryan Jackson. Ryan, you're gonna love this. I'm on 6 platforms now. I got YouTube, LinkedIn, Facebook, Twitter. Now I'm on Instagram. I'm live on Instagram right now using Yellow Duck. And Felix Sandoval's in the house. And then we're on this thing called Clubhouse, which I'm the only person in the room. But you know what? I can do it. Felix, now, Tim, you don't know Felix. Felix Sandoval is out of Colombia. You might know Ryan Jackson. You probably saw some of his public inputs in the past. We got David Englehart, and you know Steve Froming. I mean, everybody knows Steve Froming. Come on, Steve Froming. Restream.io, yes, Ryan, I'm using Restream.io, and it is fantastic. All right, so Mr. Tim Croushore, welcome to Live at 5 on 6 channels, brother.
Hey, thank you, Tom. I appreciate that. Good to be here. Good to be on your channel.
And it's good to have you here, and it's good to have David Smith. And David, you are in an airport.
That's right. Part of the codes and standards assignment that I have at Eaton is traveling around and representing the electrical industry whenever it comes to code adoption. So I'm currently in the Raleigh-Durham airport, and you might hear some background stuff going on. There's a bird flying around me just recently, and so actually, like a young mother and a very small girl ran up pretty much right to me because this bird was like hopping around right beside me. So I had to go on mute for a little bit because she was very excited.
Oh my God.
And they apologized a lot to me, and so I decided to move a little bit farther away, try to get away from the nest. But I'm keeping my head on a swivel over here because I'm not sure if I'm going to get by, some type of like running person trying to catch a plane. Do they still do that anymore? You don't really see that much of running in airports anymore, do you?
No, not anymore. There's no reason to run because you come in early.
That's right. Here I am. I come in 3 to 4 hours early so you can get on LinkedIn Live with the legend Tom
and Tim Croushore. I love it. So, I did an introduction this morning, Tim. We got Kristen Summers in the house. Awesome. That's Raleigh, right? Raleigh-Durham.
Hey, yep. And Kristen, just to let you know, the 2020 NEC is currently on track to, I believe they said, to go effective October 1st of this year.
And that's
going to be a little bit amended. And so keep in touch on exactly what's going on there. Check with your AHJ and all that stuff. But yeah, we're on the way whenever it comes to North Carolina.
That is absolutely awesome. So North Carolina is doing good. So we have a special guest, Mr. Tim Croushore. And this morning, Tim, I did an overview, and your background is very impressive. And I've known you for quite some time. And I've always seen you at the IEEE meetings, standing up there at the NFPA annual meeting. How do I represent it? Oh man, waving the book, telling them you can't be doing that. Representing the utility industry well. So thank you for joining us. And you're now, where's your PE license? What state?
Yeah, I'm licensed in the Commonwealth of Pennsylvania.
Same here, brother. I got my PE license in the state of confusion, after which I was under the state of intoxication.
Okay.
Certified electrical inspector. I didn't know that.
Oh yeah. I got that years ago. Whenever, before Pennsylvania had the Department of Labor and Industry as the AHJ in PA,
Right.
the only folks that were pushing for inspections was the utilities. And one of my previous job assignments, I was responsible for being the coordinating individual between was West Penn Power at the time and the independent electrical inspector. So in order to get a little bit of cred with the independent electrical inspectors, I took the tests, the 1 and 2 family test, the general electrical inspection test that was out there that IAEI had offered.
That's
So
impressive. I mean, those tests are really comprehensive if you think about all of the things that they require of you. And from a utility perspective, that's above and beyond because you don't do that on a daily basis.
well, I kind of was responsible for mitigating any issues between electrical contractors and inspectors from time to time. Sometimes they put the utility industry at that time in the middle. And, the AHJ didn't exist in Pennsylvania. So, the utilities were the ones that were asking for the certificate of safe electrical inspection, which was, what we commonly call cutting card. And sometimes you get into some issues that, involved, what the cutting card had to have on it and, all that kind of mitigation issues that may have happened from time to time. So I got involved in that.
Yep. And you are a 35-year inspector member of the IAEI as well as an IEEE member. So we share that a common, those organizations, IEEE and the IAEI are two, I keep telling people, two very important organizations to be involved with, and not just a member, but get involved, So
Yeah, absolutely. Yeah. You don't have as much fun unless you're directly involved and get to know the personalities. And that's kind of one of the things that I enjoyed the most about this industry was getting to meet people like you and the other electrical experts in the industry, Dave Smith and other folks. It's an association of technical people. And not only do you get to know them on a professional basis, but you also get to know them on a personal basis.
absolutely.
And I mean, it just becomes, it becomes a career enhancement or a career enrichment action that you do. So that's why I
Absolutely.
like to do it.
Absolutely.
Yeah, just very quickly.
Yep.
I was just going to ask very quickly. So you're an active member of all these different types of organizations, and as a younger guy, I suppose I was involved with IEEE HKN whenever I was back at a equivalent university in Morgantown. Let's put it that way. And so, so now that I'm living in Western Pennsylvania, I was just actually recently downloading the IEEE app on my phone because I wanted to become a little bit more involved whenever it comes to the Western PA part of IEEE. And so, can you tell me and people like me whenever it comes to either younger people or people that might have just recently moved to Western Pennsylvania, or in general maybe someone just moved from one side of the country to the other, how do they get more involved in their local IEI or IEEE chapters?
Well, I know in Western Pennsylvania, there's a Western Pennsylvania chapter of the IAEI. It meets in around the Pittsburgh area. There's also a West Virginia chapter of the IAEI, which I helped to get going a while ago. And that's that was used to be part of the Ohio chapter, but now it's, its own individual West Virginia chapter. There's also a Western Pennsylvania IEEE member group that gets around from time to time and has meetings throughout the year. And that's a great group to be involved with. Unfortunately, I didn't used to have all the time that I would go to. So I would look at the different meetings and see the ones that interested me, and I would go to those particular meetings. But those two are out there. They both have newsletters that come out, and I would suggest getting involved in the local chapters of both the IEEE and the IAEI, because you get to meet the individuals that are working in the same industry that you are.
Yeah. And I was very surprised to see you're now on Code Panel 2.
I don't think that my application's been through the Standards Council yet, but
Okay.
yes, I'll be on CMP2 as an alternate.
Well, that's still. I mean, who's the principal again? You're replacing Roger McDaniel, or no?
No. Chris Pavisi is the principal.
Yes.
And we lost the utility alternate. He took a different job or something like that, and they needed someone to fill the alternate position. And I just volunteered to go ahead and do that. I have some experience in load estimation in Article 220, and worked on some of those past things in Article 220, and it just was a natural fit.
Yeah, absolutely. Weren't you on panel 4 before?
Yes, I was. I've been on several different panels.
No one wants to keep you.
Well, no, that really is not quite true. The issue with panel 4 is kind of interesting, because when I retired from First Energy, I had to drop off of panel 4 because those are the regulations of the NFPA. And at that time, I got put back on panel 4 as a representative of EEI, funded through EEI.
Mm-hmm.
And then EEI had changed some of their associations. We got some new members in from the utility industry, and we had a new member from National Grid who had very good expertise to go on panel 4. And since I had dropped off, they put Brent Fidel onto panel 4. And then when First Energy said, "Hey, Tim, we'll be glad to responsor you back on the NEC," and I said, "Okay." And it was an issue: should I kick Brent off or just go on to do something else? And my role with the utility industry before COVID was supposed to be, I would be like the floating, past guy that would go around to the different code panels and help the utility industry representatives, with their issues during the code panel meetings. So, I applied to be an alternate on code making panel 12, which I had chaired 12 for 3 cycles. So I knew that material real well, but we have a good principal on that as well. So I was going to float between different code making panels and help out and help them. And then COVID hit, and now it's all online.
Yeah.
So I'm currently on alternate on code making panel 12 and code making panel 2.
Excellent. Yeah, David, go ahead. You're on mute. David. Yep.
Sorry about that. I'm trying to limit the background noise. It's not only utility man for the utilities, but in the baseball term as well. He's a utility man. He can fit in any position, any CMP you want. He can go from 2 to 4 to 7. It doesn't matter which one it is. He can fill any gap. It's all good.
That's good. Yeah, it's all good. And that's what I guess that's one of the key things about being involved with the process is there are people like you and in many industries. You got petrochem, you have contractors, you have labor, all these individuals who might not be on the code panel, but they're sitting around that wall listening, and then you got the coffee pot talks going on, and then you have the dinners going on, and they talk nothing but code 24/7, and it's really it gets you all pumped up. It's something really great to be involved with. We got Nihad in the house, Santiago Arias Guzman. So we're going to write an article together. I was just talking to him today. So we're going to do some cool stuff. So let's talk about the interconnected systems. So I think you did a great job in. If I'm reading this correctly, you're going to guide us through a discussion a little bit, and we created some bullet points, but you sent some slides, and I think it really takes the 30,000 foot view first because it talks about the grid, right?
Kind of does, yes, kind of does. Yeah, what you see here in this slide is when you start to talk about the interconnected electrical systems, you have to kind of look at how the continental part of the United States, is interconnected. There is one large interconnection, that's the Eastern interconnection, and that goes clear from the Rocky Mountains down through the south, down through Florida, clear on up into Canada. And there's another a Quebec interconnection that's not connected with that, but the largest grid that you would be is the Eastern interconnection. And it's a very, very large and very, very stiff system. And in that, you have different reliability corporations. You have Reliability First, which is that organization, CERC. There's a Florida Reliability Corporation. They're all making sure that they have enough generation on for the load. So that's the Eastern interconnect. You also have the Western interconnect, which is, the western part of the states. It goes California clear on up into Canada. And that's what we would consider to be the Western interconnect. And then you have the ERCOT system, or the Texas interconnection, which is Texas and a little bit of Oklahoma. And, when you talked about even this morning, the issues with the windmills that froze over and that kind of stuff, because ERCOT is a smaller system, you don't have that stability of the large amounts of generation and load, all connected together, performing the grid. And then, of course, in Alaska, you have two independent grids. One on the inner passageway, which you have most of the population of Alaska, and then you have also one that goes in through the interior of Alaska.
Mm-hmm.
So when you start look at the interconnected systems, this is what essentially you're interconnecting with in the northern hemisphere, if you will.
So let me ask you, when like you have the western, that whole yellow region on the left-hand side, right?
Correct.
And then you have the green, or then you have that little small pink section, the SPP. Okay, so would it be safe to say that if there's a problem on a grid, that it would be localized to any one of these, or are they interdependent with each other?
Mostly they're tied together through the transmission system. So depending on the size of the anomaly or the problem that could occur, it's mostly just a localized issue and doesn't take down the whole quote unquote bulk power system or the grid, if you will.
Okay. How does the PUC, the Public Utilities, was it Commission?
Mm-hmm.
How does that play into these systems and grid?
Well, most of the bulk power system is regulated at the federal level by the Federal Energy Regulatory Commission, or FERC. Okay.
Okay.
And there's also some other regulatory rules that come in for the bulk power system. Where the PUCs and the Public Service Commissions and something like Virginia State Commercial Commission, those types of things, they look at the distribution system and they look at service to mainly the customers and not necessarily into the bulk system, the bulk systems.
Okay.
Like if you go to the next slide, I think.
Yeah.
This kind of gives you an idea of the transmission system, like in the Eastern Interconnect, the Western Interconnect, and the Texas system. Unfortunately, these didn't come from they came from two different sources, but they talk about how these systems are, quote, interconnected together at the transmission voltage level. And you can see there's stuff that looks like 230 kV, clear on up to 765 kV on that slide. So because of energy security, you don't see exactly where those go, but you get an idea of how that interconnection might work in, say, the continental part of the United States.
Right. So it looks like, why the different voltages? I mean, I get it that the higher the voltages, the lower the impedances, lower the losses, right? So I can push more. Now, the high voltage direct current, I remember when I was in college, I was a Jerry's kid. I was Jerry Selvaggi. He was our power systems engineering manager. You know Jerry?
Yes, I do.
Yeah, smart man. He was working on what he called it super DC, which was superconductors, which was very like zero impedance, as close to zero as you can get, because he firmly believed in transmitting DC. Are we doing more DC in utility applications, or is it, I mean, we just use it where we need it?
Yeah, mostly what you're seeing is the AC interconnections right there, but there are DC connections, and that's where you need to transmit power over long distances, okay? And it's pretty much source to load type of interconnection for a DC interconnection. So there is some that comes like from Canada up and around the Hudson Bay area, and then down into New York area, and it's you can't connect other substations to it. It's a source supply to a DC system, transmitting load down to an AC inverter that usually puts it back onto the AC system.
Okay. And I know you're familiar with a lot of the changes in the industry with regard to more use of LED lighting, which is DC, and all these great things, which is all DC. None of that really impacts the utility distribution systems, right? You guys are pretty rock solid and set in your course with these voltages and AC voltage and transmission. Would that be?
Yeah. Yeah, I would say for the next, 50 years, it's probably going to be that way. Now, going further, I can't tell you if I had the crystal ball, I'd know what to invest in. But right now, pretty much the AC system is what's giving us the integrity and stiffness, of the grid, today. Going over in the future, with power electronics, DC, more efficient energy conversion, battery type energy storage, those types of things. They are all impacting this system, and some in a little way and some in a great way. So, it's going to be a continuously evolving system.
Cool.
Okay. Well, this is a little bit of discussion of the Hawaiian system. Okay, so we have some territories. Hawaii is about the only state that has an islanded system. Of course, we have the territories of Guam, that American Samoa, Puerto Rico, and a few other ones like that. But
Yep.
those would be considered like islanded systems, in that when you look at the Hawaiian Islands, each island is independent of the other one, and there's no transmission lines between in the individual islands of Hawaii. So they have to have generation to match the load on each one of those islands. And if you go on to the next slide, I took this picture at the top of Diamond Head looking back towards Honolulu. And, that's Waikiki Beach that you see where the ocean meets like kind of the city. It's really kind of a neat place because it's one of the few areas that you have that kind of heavy commercial type of load, high-rise buildings. There's a large low voltage secondary network that's in there. And, even in the distance, you see where Pearl Harbor would be and things like that. So this would be an islanded system. And the smaller the systems, the more issues they have with interconnection.
Uh-huh.
And the reason is you don't have that stiffness and stability of multiple generators, going load. So smaller issues on those systems can impact the overall portion of the grid. And especially like, this is the island of Oahu. Like on that island, you have, fairly high electric rates because most of the electric generation there was oil. And you have a lot of people putting on solar. And at some points in time, you have more solar energy than you have load because of the daytime. And at nighttime, you have more load coming back on when the sun doesn't shine. So it becomes an issue there. So we see a lot of the early issues with islanded systems coming in the island of Hawaii or the islands of Hawaii, in interconnected systems. So, we're learning a lot from interconnection from the problems that they have in some of these smaller areas.
Yeah, and to your point, they're a smaller infrastructure from a generation presence from a, I guess, what did you call it? You call bulk power, right? Bulk
power system, yes.
Yeah, so a bulk power system, that would be like a power plant, like a nuclear or fossil or something like that, right?
Well, the bulk power system has the generation connected to the transmission and subtransmission systems. Okay.
Okay.
So when I talk about bulk power, generally you don't have many customers connected on the bulk power system. You may have a large steel mill, or you may have some aluminum smelter or something like that that uses multiple megawatts of power connected to the transmission system. But mostly the transmission system is to take originally when it was designed, take from generation and then supply down to the substations, down to the load where the end users are.
Gotcha. Okay, gotcha. And okay, so I'm going to look real quick because we're getting some comments over here. We got Nihad El Sharif, Tamaki Ono, that's Japan. So Japan's in the house. Santiago says, will you discuss IEEE 1547 and momentary cessation occurrence?
Yes, I can do that.
Awesome. We'll hit that. I'll make a note of that. Well, I'll just remember to go up in there. Jean Hernandez, nice to see you on YouTube. So Ryan's saying over there in central Utah, you got a 500 kV to Southern California. Wow.
Yeah. And the issue is California is a state where it's basically the generation is not in my backyard. So it's a NIMBY type state. So they put the generation out in the desert and some of those areas, and you need to transmit that a large way. And Ryan, pulled that up really quite well as you transmit it from 500 kV DC from that generation that's outside of California back into California to be able to serve those loads.
Yeah, we got Robert from Omaha in the house. Thanks for joining us, Robert. The future will be a combination, and DER will play an imperative role. DER, distributed energy resources. So that's what we're really getting into this whole discussion. So what we're doing right now is we're talking the big scale. You're talking, and I think that's why Hawaii, and correct me if I'm wrong, you're saying Hawaii is important because the infrastructure, the generation is much smaller and it's islanded. So the impact of anybody who, if you start to rely on distributed energy from either homes or businesses, now that relationship is getting to more of a, and what I likened it to, I had another conversation when I went live on Instagram. for the first time this afternoon because I was testing it out at lunch. And I likened it to a grocery store. Okay, so here's my analogy, Tim. You got a grocery store and you own a grocery store and you're putting food on the shelves. You know people are going to be coming to your store for certain food, right? And you keep it supplied so that when they come for eggs, they come for bacon, whatever it is. But then all of a sudden, everybody says, a bunch of your customers say they're going to have their own farms. They're going to grow their own meat. They're going to grow their own eggs. They're going to grow their own produce. Now, all of a sudden, you're not getting them come to the door as often. But would make it worse is if they say, hey, I'm going to start bringing food in to sell on your shelves, right? I'm going to bring my food to your store. Now you cut off those ties to the suppliers who were bringing eggs because, Aunt May down the street, she's bringing in thousands of eggs a week. So you don't need to buy another supplier. And then all of a sudden, Aunt May says, I think I'm going to retire. I'm going to quit. And you go, hold on, you can't, because now I'm relying on you for those eggs, right? I got people coming in here looking for eggs, and I need you now. So that all of a sudden, Aunt May's little hobby turned into a real business, and now other people rely on that person. And when they're gone, things start to collapse. And I would almost argue that your distributed energy, when you start relying on all of the residential units or commercial people to supply power to the grid, and you start backing off, or do you back off from a utility perspective?
Well, I tell you what, maybe this is a good time to talk about IEEE 1547.
Yes.
Go ahead and slide with the new and the old IEEE 1547. Maybe that's a good.
Yep. Wait, hold on. I got to find it. Let's do this. While I find it, I'm not going to get, I don't want to get too many people dizzy. There we go. All right.
Okay. The original IEEE 1547, I believe, came out in 2003, and the new version, or the current version, came out in 2018. And the big difference was a change in philosophy with how to deal with I'll call them distributed energy resources, but alternate generation or whatever. And, the IEEE 1547 document is really the ruling document for interconnection at the distribution level, okay? It's not at the transmission or sub-transmission level. In fact, there is an IEEE working committee, that's IEEE P2800, that's dealing with these larger, bulk systems. But this is more in the distribution system. And the big difference between the old and the new was how it handled anti-islanding, okay? And what ended up happening is that in the old system, the utilities got together with the inverter manufacturers and with Underwriters Laboratory, and we worked a lot of this stuff out that said, hey, if we have these distributed resources, they were very small at the time, and if you had a trip on your distribution system, we kind of wanted those small generators to kind of get out of the way, let the utility distribution restore if possible, or sectionalize and take care of the issues as possible, and then put the power back on so that anytime you had loss of voltage or change in frequency, that those systems would trip off a line, the utility would come back on, the inverters would stay off for 5 minutes, and then they would come back on, and everything would be fine if the power was restored. In the new system, there is an issue that they call ride through, okay? And throw on to the next slide. See, the issue came in is the original settings for the IEEE 1547 was based on the Eastern Interconnect. And there was a large Electric Power Research Institute, or EPRI, as you can see on the slide. They did a study called the Distribution Power Quality, and they looked at what was normal on the distribution system and what was abnormal on the distribution system, so that your inverter-based generation would be set basically if the system went outside of normal, it would trip off. Now, what happens is with the 2018 version of 1547, they are asked to hang on for a little bit longer, depending on what would be normal or abnormal for a certain period of time, both in frequency and in voltage. Now, on the larger systems, frequency is pretty rock solid. You know, when you start talking about 60 hertz, it doesn't vary much above 60 hertz. So there are frequency settings, high and low, which would say what's abnormal. But what ended up happening in California was we had some of the larger generation, the inverter-based generation was based on the 1547 settings, and there was a trip on one of the 500 kV lines that caused the voltage to go low in those areas. And what ended up happening was it tripped off several hundred megawatts of solar generation at the same time. So you had some anomaly occur on a 500 kV line that caused a dip in voltage that took a normal fault sectionalizing section to a greater problem of losing a bunch of generation at that same time. And the Federal Energy Regulatory Commission, the Reliability Commission said, hey, this is not a good thing. If we have these trips or we have these anomalies that occur from time to time, either from a fire or from lightning strike or something like that, we don't want to lose a bunch of generation. So that's when the new version of the 1547 came out. A lot of work went into, what needed to ride through, if you will, some of these anomalies and what would be for anti-island protection. The issue comes in, though, with anti-island protection on a smaller system like Hawaii. You get a lot more frequency variations and you got a lot more voltage variations than you do on the Western, the Eastern Interconnect, or even in Texas, okay? So that, those settings for that system have to be a little bit wider than the settings that may be for some of those other types of systems. And that's a lot of the work that's going on now at the Public Service Commissions, is determining on what those settings should be. I've always been a proponent of keeping common settings so manufacturers like yourself could know what to set for these systems, because it's a grid dependent type of setting systems. But again, there's a lot of work going on. And the last time I was down at FERC headquarters in Washington, D.C., we were still discussing this. And I haven't really followed on with since 2018, where we've come together with our settings. But again, this is stuff that can be put into your UL 1741 inverter. I know Tim Scanina from UL, who is the main proponent for UL 1741. These inverters can accept a wide number of settings, but it's what that setting should be for that proper location in the world, or actually anywhere.
Right.
Does that make sense?
It makes sense to me. How about you, David? Clear as mud. David in the airport. I hear you. Jean Hernandez, he says last year he had a 1547.1 related to testing. What's that?
Okay, 1547 is the specification for how the testing should be done for those inverter-based systems. That's what goes into UL 1741. So 1547 has a family of standards that go with it. There's one on microgrids, there's one on testing, and then there's a number of recommended practices that tell how this stuff should interact and interface. I didn't put that slide in. I don't remember what the individual dot functions do, but I didn't figure we'd go down this path. But anyway, the dot one is the testing standard. So 1547 is a standard. The dot one is a standard. The other ones are generally recommended practices on how those interconnections would occur.
I'm wondering, Tim, in 705, remember Article 705 of the National Electrical Code, right? 705 is the interconnection. So that is titled Interconnected Electric Power Production Sources. We don't talk about testing these systems, do we, anywhere in 705?
Well, yeah, actually we do. Okay. Let me open my 705 and I'll kind of walk you through how that works. Okay.
Yeah.
See, Underwriters Laboratory puts out product standards. Okay.
Mm-hmm.
They're the ones that are putting out the UL label for the product standards for the products that you go out for. So when you look at the scope of 705, okay, it's in 705.1. It covers the installation of one or more electric power production sources operating in parallel with the primary sources of electricity. So 705 is just covering the installation. The IEEE documents are covering the interconnection workings, and 1741 is covering the product standards. So all of those work together in order to you know,
Yeah.
to make the installation correct.
Yeah, and you know how I reference that often as I can't remember where I stole that from, but it's like the three-legged stool. You need all three of those. You need the codes and the standards, you need the enforcement, you need the installation requirements. So you need the standard for the product, and they do all work together. Um, and now Jean Hernandez, while you're trying to get your book, and now you can provide reactive power support, right?
That is correct. The new version of 1741, the biggest change was in the settings for ride through. The second part was in the older versions, people just used to put out watts with the inverters, but now the inverters can put out both real and reactive power. They can push bars into the system and they can suck bars from the system. Now that setting would be pretty much on the local utility side, whether or not that local utility distribution system would need reactive volt amperes or would need that system to draw reactive volt amperes, so they can actively regulate voltage.
Excellent. So, Jean Hernandez, you are on the ball out there on YouTube land. Santiago says the problem rises when the computation of the parameters goes wrong. Take the blue cut fire event as an example.
That's exactly what I was talking about on the bulk power system, the blue cut fire.
Oh, so that was your example. Okay.
That's the one.
Okay. So, and Ryan Jackson is out there thanking you for the stuff you did in the 2020 code in 705. I'm going to go back up because I'm missing something. David Shapiro is out there on LinkedIn. He says, nowadays, I dare say worries over overuse, undercapacity, more localized incidents that are due to traditionally predictable operational failure are less of a concern than hacks and ransomware. Oh, so he's talking about the cybersecurity. Um, uh, yeah, so what he's saying is that a lot of these localized issues that we've dealt with in the past aren't anymore as much of a concern as what we're seeing from a cybersecurity perspective, because they could really lock you down, like what happened in that was in Texas too, wasn't it?
I believe
The
that
pipeline.
was an electric utility. There have been cybersecurity regulations that have come out from the federal government that the utilities have to follow. And essentially, there's no external pipe to their control systems from an internet-based system. So I actually was national, let's see, what does NERC stand for? I was NERC, Critical Infrastructure Protection Secure. So I had to take tests to get a background check and everything else to work in the control center. But again, the control center, the power system, the control center, and the computers are in a what they call a 6-wall enclosure, meaning there's no external. I mean, it's an air gap type system, and there has to be 6 walls. 4 walls on the side and a roof and a floor to where that would be able to get into. And what ended up happening was you don't have any direct input to the control system, but those control systems every now and then would spew out data out to the system. The folks would be able to watch what was going on. So the only thing that you can do with the control system of the utilities, or at least the electric utilities I was familiar with, is just be able to monitor it. You can't control. You have to be in the control center in order to do the switching and the controls. Now, I'm not saying that, you couldn't do something more on a local basis with, say, an individual substation or a power station,
Right.
some terroristic act. That might be able to happen. But again, not from an external hacking environment that
So
can occur. And that's the utility spent a lot of money in order to get it that way.
okay, so I know you are involved with the 2023 process. So I want your opinion on what do you think about the cybersecurity public inputs to the National Electrical Code?
I think they're very critical. And the issue comes in is, cybersecurity, just about everything operates off the internet. And, people like to work from home. You like to be able to connect on to a corporate system. And the problem comes in is, passwords and accounts can be hacked, and somebody gets in and do nefarious things.
Yeah.
And there are, the federal government does have some guidelines out there, quite a number of guidelines on how to protect against that. The problem comes in is, it gets to be expensive to make sure that you have those controls and those protections in place. But again, it comes down to the point of, is your service or your product that you provide, is it part of critical infrastructure? And we found out that, the oil pipeline was part of critical infrastructure and, really needed to be protected. So, we have something on the electrical side of that with the, Article 708 with critical operations power supply. And of course,
Yeah.
hospitals and healthcare have something different. So I think that cybersecurity may not be the right place in the National Electrical Code, but it's certainly an issue that needs to be dealt with.
Yeah. Now, when you talk about, like, when you get into distributed energy resources and you're relying on my house, possibly, right? I mean, I could influence the grid or at least my local, could I influence the grid? Let me ask you that.
Well, if you have one of the inverters and you push more bars into the system, you have the opportunity to regulate voltage. So, many times you might have, maybe in your house, not necessarily, but you may be on a common transformer.
Right.
So if you push bars into the system, you raise the voltage on your neighbor, that's something that you could do, probably on that size of a residential system. Residential systems are probably not more than 25 to 30 kW in size. Now, the larger you get, the larger the impact that you have. It's, the old story is, if you pee in the ocean, you don't have much impact, but if you pee in the swimming pool versus peeing in the kiddie pool, it's different types of impact that you'll have.
I love that. See, a man after my own heart. Analogies say it all. They say it all. So you were talking 705 and whether or not you have to performance test when we were mentioning earlier about I think it was Jean Hernandez was saying that they had to do the 1547.1 testing, and we were talking about how you had to demonstrate and whatnot that equipment how do we get that done in 705?
Well, generally that's going to come down. It's not necessarily an issue in 705. Mostly the National Electrical Code and IEEE 1547 are into regulations into most states' requirements. So, the utility system, of course, they're a statutory entity. So the utility system becomes an AHJ. For those of you that maybe not know that, there are statutory regulations that give the utility the ability to say what those settings would be. So depending on the system where that's interconnected would be that you would have anti-island settings, and you may have the what they call volt watt settings or active power regulation settings that may be available. So usually the utility is going to communicate what those would be. Now, there are performance testings that are required. For the smaller systems, the utility would certainly like for UL to say, for the UL has also often talked to us about, hey, give us what your settings will be. We'll tell we'll tell the manufacturer and we'll test to those exact settings rather than the range of settings.
Right.
But the larger you get, you may have to have some performance testing, and that's where you would find some other type of third-party testing organization that may be pushing that and using IEEE 1547.1.
Gotcha. Okay. Now you mentioned islanding, and do you want to talk a little bit about microgrids and that system interrelation? You had a couple images associated with that. I don't know.
Sure, I'd be glad to. Go back to the one where the beginning of those slides where we start talking about what typical generation was in the utility system. So go back quite a few. Let's see, right after the black, next one. This basically says that the utility system has lots of distributed energy resources coming.
Gotcha.
So it's a migration. I think this confirms what everybody else has been saying, that it's not just going to be centralized generation. There's going to be all sorts of on-site generation. And you have a slide of solar, you have a cat diesel system, you have windmills, you've got a combined heat and power system, solar cells, energy storage. You have different types of solar.
The other aspect, which isn't on here, is your electric vehicles nowadays, right? They're talking about those being able to supply power.
Absolutely, absolutely. That's why Code Making Panel 12 is dealing with Article 625 and how that's going to be. And the vehicle can put out power in a couple different ways. It can put out power through the electric vehicle supply equipment, and it can also put out power like a regular generator might be, a portable generator. So you have both of those, types of systems that would be there. I've seen, some vehicle ads where, the guy takes his truck and he powers a bunch of festoon lighting off of it.
That's exactly
And,
right.
it's kind of like a standalone system, if you will.
Yeah.
So, I mean, this is all things that, we've got to think about in the NEC.
Yeah, and I know there's a lot of there's dialogue going back and forth, because I think it was panel 12, and I believe it's panel 12 that talked about making the receptacles on these vehicles GFCI protected, because, to your point, they're provided. But here is the thing, like I'm in the market now. I'm looking for a vehicle, and we were looking at pickup trucks, right? And on the back of these F-150s and Chevy trucks, these are gasoline engines, right? They have inverters and they have receptacles. They've got the tailgate that you work on. But the code is not covering anything about a gas, like that type of a vehicle. This is just an electric vehicle, but you have the same problem, or the same question. I won't say problem, because I would have to say question on all of these vehicles that have onboard receptacles that you're plugging into and using tools.
Yeah, absolutely. But the thing of it is you got to be careful with, the vehicle typically has been under another standards development organization,
Right.
not necessarily the National Fire Protection Association, but the Society of Automotive Engineers. And they have very similar requirements for their, types of systems. And it becomes somewhat of a little bit of education and a little bit of, sharing of information, because, what the automotive manufacturers have said on Code Making Panel 12 is saying, we appreciate what you're saying here, Code Panel, but again, we want to make sure that this, the SAE documents provide this same type of protection and the same type of shock protection like a ground fault circuit interrupter would do, and those types of things. So it's, it's a little bit more complex, and unfortunately or fortunately, as the code goes, is the NFPA doesn't have all the driving standards organizations that we have electrical codes for. Industrial machinery is NFPA 79, and you have to tie in with Article 670, and you have NFPA 99 and Article 517 for hospitals and healthcare. But elevators, escalators, moving walks, that's a different SME document. SAE covers electric vehicles. IEEE 1547 covers those utility interconnections. So it's, it's a handshake, if you will, between these standard organizations that everything kind of works together. And, even the voltage standards, it's a NEMA committee that's, ANSI C84.1. And, those go with and you have to have good representation from all the stakeholders on all these committees.
Oh, exactly.
just to make sure that stuff works and functions properly.
Exactly right. And I've used that analogy myself as well. It's a handshake, and like we're talking about interconnection, you're reaching your hand out to the utility saying, I want to be a partner here. Even if you're putting your local generation and you just want to supply your loads, if you are connected in parallel with the utility, you can influence, like you said, the voltages, because if you start putting VARs up onto that system, etc., you can interact with other people around you. And that needs to, once we follow all those standards, and I think that EV discussion is really paints the picture, because like you said, the National Electrical Code does not apply to the electric vehicle, what's on and in that vehicle. That's a different standard. The National Electrical Code doesn't govern what I put in a switchboard, right? I have the standards for switchboards.
Right.
You make sure that it's listed to the right standard, then you install that piece of equipment the way you're supposed to install it. So they all do work together, and it is it's like a partnership between everything, but everybody's got to do their part, right? So
Right. Mm-hmm. Okay, go to the next slide. That's kind of in the mind of a distribution engineer. But here's some of the things with that causes the utility issues with interconnected generation. First one is designing the distribution circuits. The engineers that are doing this are looking at the conductors, the equipment, the transformers, the regulating equipment. They're looking at this from minimum loading, the maximum loading, and what we call 8760 loading, which is 24 hours a day, 706, 24 hours a day, 365 days a week, 8760. But the issue comes in is when we had non-generation, you could pretty much say one residence was very similar to another one, and you could kind of lump them together, and you could balance your circuits because of the load. When the weather got warm, air conditioning came on, or when the weather got cold, you might have heating equipment that came on and that type of thing. But what ends up happening is when you have interconnected generation, because it's an optional thing on homes, is you get into what we call circuit unbalance. And you have so many homes on A phase, so many homes on B phase, so many homes on C phase, and it was pretty much a home is a home is a home, because
Right.
Water heaters and ranges and that kind of stuff are pretty common. But now you can get some subdivisions that you might get, have a lot of south-facing roofs and you get a lot of generation. Now you've got to worry about your circuit balance between A and C, A, B, and C phase, and your loading on the system. And you want to look at your bar loading. You want to make sure your power factor correction is correct, just so that the system operates correctly and everybody receives the right voltage and things like that. And then again, the protection comes into it too, is when you have so much generation, the distribution system was really never designed to have generation on it because it's kind of a substation to load from the distribution feeders. Now, when you have generation on it, you have a short circuit current flowing from the substation onto your feeder, but now you have the potential of short circuit current flowing from your interconnected generation into the faults as well. And depending on where that generation comes in, you can overduty some of the equipment that's on the utilities distribution system because it's the same issue as you have premises wiring systems, too much short circuit protection. And then, the supply voltage, you're worried about supply voltage, you're worried about the quality of the inverters, and most of those are taken care of with the current standards for harmonics and flicker. And, you want to make sure that you have the right capacity for your circuits and your transformers. So it becomes a whole different way of thinking about your systems. Again, when the distributed resources, the alternative generation or whatever was small, wasn't a big deal. But the larger it gets, and it's going to continue to get larger because people, hey, if I have an electric vehicle, why don't I put solar cells on my house? I'll charge my electric vehicles with my solar cells. There's a lot of disenfranchisement with the utility system. Says, hey, I don't want to pay for the utility. I'm going to put my own system in. That's great. But we've got to be able to accommodate that. And, it's kind of a party line system. And you got to make sure that everything functions. And, when it doesn't function, you get into reliability issues, and people don't like to be out of power. People, and different things like this. And I won't talk about what the acronyms mean. Most people don't care about them. But, I can certainly talk about them if you really, really want to know.
Yeah. Well, we'll see if anybody chats and says, I want to know, or they can Google it. What's going on, David?
So I just want to make sure I heard something there, but I know what it is. I want to see if there's anybody out there that doesn't know. I heard the term party line system. I don't think people from my generation and younger would know what that is if I didn't listen to my grandparents and some of their stories.
Yeah. Okay. Well, you see me gray hair, just like, what I mean by party line system is, pretty much everybody in the distribution system is in there together. And, when the circuit goes out, everybody goes out. And, if the circuit has high voltage, a lot of people have high voltage, and you still got to deal with voltage drop and other things like that. But that's what I mean by a party line type system. Sorry, David, for
and
us old folks,
I knew what you were talking about, but there might be some people out there that actually we're getting to the point where that they don't even know what the floppy disk icon means anymore. At least what it used to stand for, I guess, right?
Yeah.
Santiago says, does the regulations say something about how to check no generation is in a circuit due distribution generation?
Okay, generally how that's done is when a generator wants to come online with utility, they send in an application. I know what they did in First Energy for what they worked on. They mapped all of them and they mapped the size so they would know in order to do that. And that mapping also went part of the modeling system. Now they used an Eaton product, if you will, to do a lot of their circuit modeling. And, that was the SIME product. And, it took in consideration generation, took in consideration substations and things like that. So, you know, it's the same thing what you were talking about with your SKM power tools. It's a very similar modeling system, and it models all this kind of stuff. And the thing of it is if you have your model correct, it will replicate what the system is doing out there, and you can make proper designs. But if you don't have it modeled correctly, you're just guessing at stuff, and you're listening to customer complaints as they come in to saying, hey, my voltage is out of whack, or I've got too low or too high, or some
Right.
type of problem like that.
Right. Now, NHZX Boy says he has an inverter stay on when the utility dropped out, and he said he required a firmware update. So, and he's wondering whether or not if there's a bunch of those things out there, and if they're near each other, could that? I mean, that could create a problem on the distribution system as well, right? I mean.
Well, I think what he's talking about is a multi-mode inverter.
Okay.
Now, multi-mode inverter, and that's covered, I think that's in Article 100. Let me just make sure that it is.
It's either there or 690.
Yeah, no, it's on page 37, multi-mode inverter. Essentially what a multi-mode inverter is, and I haven't gotten to the slides where I've kind of talked about the early interconnections versus the newer interconnections.
Yeah.
Go a couple slides. And let me try to cover multi-mode inverters. Okay. In the old days, okay, when I first started with the code, okay, we had several different articles dealing with standby generation. The reason why people had generators was to have standby generation. The utility wanted a way. They had either critical loads or they wanted to have business processes that would work. So you find Article 700, 701, they were your legally required standby systems. Article 702 was your optional standby systems. 517 was your hospital healthcare, and 708 was your critical operations power supplies. And essentially that you had your critical loads that went through an automatic transfer switch. You're on utility for a period of time. And if the utility had a problem, the automatic transfer switch would flop your critical loads over to your generator. And in a hospital, had to start, I believe, within 10 seconds, if you will. Yep. And you would have your critical loads back up in operation. So, we morphed from that. And we also in the computer industry where we had uninterruptible power supply systems where we had, the utility came into like what would now be considered maybe an energy storage system. And the batteries would provide power to the critical loads, okay? Mm-hmm. So that you would have an isolation. And, previous to the Energy Policy Act of 2005, the utility system said, hey, our distribution system isn't designed for this generation. You can't put it on. Well, EPAC 2005, the Energy Policy Act, changed all that. So the utility industry had to work to understand how to make interconnection of remote generation possible. So I worked a lot on that, in my career. So go ahead and go on to the next slide. Okay. So what you have with an interconnected system, this is the Article 705, or something that Tom, you and I worked on, the 231 draft, which you'd have an interconnected system where you'd have some type of combined heat and power system. That's that gray thing that you see, and you had some solar cells on a home. And the UL 1741, converter, if you will, basically would allow those to be in parallel with the utility. However, when you fall on the utility system, everything would drop off. You would lose your ability to, supply power to, your critical loads. You're going to go, gee, I have all these solar cells, but my power's out. I can't do anything with them. So we go on to the next slide. Oh. That's fine. We have, a microgrid type of system, and that can be constructed out of a multi-mode inverter, or it could be through a microgrid interconnect device, or the MID. And these are all defined, systems in Article 705. The multi-mode inverter basically allows the interconnection to occur. But if you would lose the utility, it also provides power from your solar cells or your batteries into your loads. So that multi-mode inverter would have certain critical loads, tied off of it. Same thing with the microgrid or the microgrid interconnect device. Go to the next slide.
There you go.
Yeah, okay. Build this slide a little bit. Here's the general interconnection. This is what's in 1547. Okay. Keep going until we get the critical loads and the non-critical loads. So here in a microgrid interconnection, we'll have something called a microgrid interconnect device. And go ahead and click that till it comes in.
Here it is.
So the microgrid interconnect device allows the distributed resources, the solar, the wind, or whatever, to be connected to the utility system by normal, but it'll also isolate the critical loads, kind of like an automatic transfer switch would be if you had a fault on the utility system.
Okay. Hold on. When you have the DR over there on the right,
okay,
that's your distributed resource, which could be wind, solar, battery, whatever it would be, right?
Energy storage, anything.
Anything.
Yes.
Okay.
Okay.
And then you have loads that are being supplied both from the utility service, right?
Right.
That's on when now the mid what is it? Microgrid interconnect device, right?
Device.
Yeah. So that mid is that dividing line that basically would that be my PV or my disconnect for the system?
Well, if you think about a mid in this configuration, it's kind of like an automatic transfer switch that both sides are closed. Okay. If you think about it that way. And when you have a fault on the utility system, the mid detects that, and you generally want to have enough generation on with your critical loads, or bad things happen. If the DR doesn't match or the energy storage doesn't match, you can't match the critical loads. But the mid would open up and supply power to the critical loads.
Right.
Now, when that fault that you see on the utility system, right, called the area electric power system, or the area EPS, when that fault goes away, you have to reparallel that island that you've created, that microgrid, with the with the utility system, and to have like that bumpless transfer. It's uses a lot of the concepts that we showed in Article 701, 700, 701, 702 have that bumpless transfer, but it allows for the connection to be continuous. And somewhere on there's a utility meter that is going to register whether the power is flowing to the premises wiring or from the premises wiring back onto the utility system, distribution system, or however it's interconnected.
Excellent. Okay, I get it. Now, David, I know you've got to connect. You're in an airport right now, so are you going to tag out?
Yes, sir.
Okay. What we're going to do is when you shut down, I'm going to Tim. I'm going to have to just do something real quick. So bear with me. So go ahead, David. Thanks for joining us, brother. Always.
Everybody, thanks for coming on. Tim, this has been fantastic. Can't wait to meet you in person. Tom, thanks very much for letting me come on. Everybody, thanks for signing on. Don't forget to, whenever we get done here, hashtag Eaton Tech Talk on whatever platform you're using. You're able to find all of the former episodes we've been having. And for me, signing off from Raleigh.
Awesome.
Take care of you.
Thanks. All right, Tim, I'm going to, I think when I lose him, yeah. So hold on. I'm going to fix you. I'm going to fix you, brother. This is what we do. This is what we call live. And some people have studios and all this good stuff, and not me. No, I don't have studios. Oh.
I'm actually in my third bedroom, so see my picture of Bryce Canyon in the background.
I love it. All right, so let me see if I can get this back again. There we go. Now I think we're okay. Hold on. Got to get my guest 2. He was guest 2. Yeah. Let's turn that. Boom. There we go. All right. Go ahead. Sorry about that. Now, okay, so Yeah, that does. All right, we're back in gear now. So we have our microgrid interconnect device. We've got that micro. What's the job? That's going to be listed as a microgrid interface device, right?
Yeah, now that's the issue. That's what's currently going through the UL 1741 committee is, dealing with the requirements of that microgrid interconnect device. Now, previously, that could be any number of things. That could be a circuit breaker with proper relaying. That could be a power electronic device. That could be a number of different things that's in that mid, okay? And we wrote it specifically to the point where it doesn't depend on the type of technology that could be. But that microgrid interconnect device, to have that microgrid, has to be a listed device, but the listing requirements aren't completely solidified in UL. There's an outline of investigation. There are some other things that are out there, but that currently there isn't a section in UL 1741 that deals with that mid, at least not within the past couple of months. That I was involved in some of the committee discussions. So
Right, right. Now, Robert from Omaha on YouTube is telling us multi-mode inverter current mode when power company available, switch to voltage mode when power is not available, also anti-islanding. I'm not islanding. I'm not sure what he means by that.
well, essentially, the mid device or a multi-mode inverter
Hmm.
allows the interconnection to occur, but it will not, if the utility goes away, it doesn't feed fault current back into the utility system, but it will be able to supply loads, and it goes to, supplying voltage and driving the voltage in order to power the loads. Generally, the current source inverter is going to push current back into the system at the utility voltage. But now the inverter itself is now acts like an uninterruptible power supply system, has to supply both voltage and current to the critical loads.
So, but the mid is
I
not
get it. Yeah.
the mid's not a device that would make sure I don't overload my panel board, right?
Well, the mid, again, it's a microgrid interconnect device. It allows, it's one technology that allows a microgrid to occur.
Right.
A multi-mode inverter has all these functions built into the inverter itself.
So the multi-mode inverter could be a mid if it's listed as a mid.
Correct.
Okay, so it's not like I'm buying this little black box and I'm going to put it in there. It could be that my inverter is also doing the job and the function of the mid, which primarily is really worried about things like frequency and voltage fluctuations and things like that, right? Not necessarily how much current's going on to the panel board.
Right. Now, what I showed here, this is an AC microgrid interconnection. Through the multi-mode inverter, typically you're going to have DC output into your multi-mode inverter from your photovoltaic cells, but you might also have AC power coming from your energy storage system into that multi-mode inverter too. So you've got to have a system that's designed for whatever input that you have to be able to supply 60 hertz power to the loads that you want to supply.
Gotcha.
It's complex, but the power electronics these days. I heard you talking about the new adjustable speed drives or the variable frequency drive this morning. Hey, power electronics have been really enabling this type of technology, and the sky's the limit on kind of what you can do. You can take a DC source and make AC, synchronous AC. You can take a DC source and make asynchronous AC. You can take an AC source and make synchronous or asynchronous AC. I mean, all sorts of different things that are out there.
Yeah, and our newest product is doing it in the smallest package that you can get it in. So it's just amazing how technology has taken off.
Yeah, especially in the power electronic field. Yeah, absolutely.
Now,
and I mean, you guys are seeing this thing with the issue in panel 2 with the power electronics and the the AC HVAC systems.
Yeah.
There's some issues there with I saw with AHAM and some of those things. So even though you have those capabilities, there's sometimes unintended consequences that come out too involved with it too as well. So it's an evolution and a learning process for everybody involved.
That is exactly right. And like you said, and that's like the GFCI relationship with an appliance or an HVAC unit. It's that you weren't thinking about it because there wasn't anything in the standards that says, hey, can I put current on the grounding electroconductor? Well, sure, yeah, I'm going to do that because it's part of my design, because I'm not pulling a neutral. And then all of a sudden you go, oh, wait a second, now you want to put GFCI on it? Oh, whoa, that's a problem.
Yeah, when your GFCI is in 46 milliamps and you're putting more than that into the grounding conductors.
Which, by the way, violates the NEC anyway, because you're not allowed to put that much current on that equipment grounding conductor, right?
Well, that's right. I mean, that's where the product standards came in and said, hey, you can use it for voltage sensing and, a few microamps or something like that. But now, you find, like I said, it's this unintended consequences that come out, especially when you want to push safety too, in for like GFCIs.
Yeah. Now, Logan Millington has a good, now, you know what? Here's what I've learned, Tim. These guys come up with the question. So Logan's out there on YouTube. He says, what if you want to power 2 buildings from the microgrid, but the 2 buildings each have their own service? So I've got 2 structures, 2 buildings, 2 services. I got, Bob, we have my cousin has a house right next door, and we're going to put the grid outside, right? I've got like, we've got some wind, we've got some solar, and we've got a nice little micro system going out here, and we're going to supply both houses. What do you do?
Scratch your head a lot. No. No, actually, some states actually deal with that in the ability and what they call that community power, I believe. And it allows, essentially they put power on in one, and they have some type of intertie with the other, with the metering system and the utility. And there's some states that allow stuff like that to occur. The issues come in now is, you're supplying power onto the utility system that's supplying power to another system that may be coming from a different area. It requires a lot of thought process in how that could occur. So a lot of utilities aren't real fond of that happening, but I know there are states that do permit that. And, it is a possibility. Now, the issue comes in is from a safety aspect, and it's always been like, hey, when your neighbor's out of power, can you run an extension cord over to them and that type of thing? When you have some type of hardwired connection in there, you have 2 service interconnected through premises wiring, and that's really a safety issue. But again, it's possible. It's, like I said, requires a lot of head scratching and figuring out what the safety issues are in that type of configuration, but it can be done.
Yeah. And now, an NHZX boy brings up an interesting, as he was out there cooking hamburgers, he says, I may have missed this, but he's asking with these distributed systems. So now you've got the distributed system, you've got the utility, you're interconnected. Is there a danger of not knowing who the boss is with regard to who's controlling the frequency, who's controlling those different parameters? I think that's basically what we're talking about, and that's what the standard is doing. It's trying to regulate that or control and say, this is how you're going to play, this is how we're going to play, and establish the game rules, right?
Right. And generally where that comes in is that's where your public utility and public service commissions come in. They are ultimately responsible for the rules and the requirements of, whether you have net metering or not, or whether you have community power or not, or those types of things. They're the ones that are going to say what the rules are. And then what they do is they delegate down to the local utilities into, implement how you would necessarily implement that. And they would let the approvals or, non-approvals, come down to the local utility. This is where where I talk about, a lot of people, cringe when I say the utility companies and authority having jurisdiction. They do have statutory authority for a certain scope of work that they would be in. And that would be safety, voltage regulation, frequency regulation, interconnection standards, and things like that. So that's why there's an application process with the utility. And you can come up and we have seen really some very nice installations and some really ones that are like crazy that, basically you have to come up with a technical reason why not to approve them, because they do, give some type of issue out on the system. And that was been a lot of my work and a lot of my career too, is, trying to figure out what was right, what was wrong on some of these things.
Absolutely. So this is another example of a mid being placed in a system where you have your grid. So that's the utility system up there.
Right.
You now the generator, the wind, the PV. Now, let me ask you a question. On you drew a generator. We got a generator there, but I have never personally in my history seen a generator operate in parallel with the utility. I always see a transfer switch.
Okay.
So, I mean, I mean, when would somebody run a generator in parallel?
Well, the typical ones that are done like that are the combined heat and power. Okay. Um,
Oh,
Essentially, CHP, or combined heat and power, is a very expensive heater or a very expensive water heater. Okay.
you know what's
So,
funny is I just had a flashback from our phone call a while ago. You explained this to me. I feel like an idiot. I love it because when you said that the heat, and I was like, I never realized that stuff existed where the generator is generating the heat also for the facility, right? And you're pulling that power off of there.
well, you have some type of prime mover, some type of internal combustion engine, and you're circulating the water through that to provide hot water, and that generator itself is providing some base load for
Yep.
that facility, and that's where you might have something like that. Generally, that interconnection requires relaying, and most utilities will require some type of utility grade relay, either a Schweitzer type of relay or a Basler type of relay for that AC interconnection. Um,
Right.
we see other generators like that where you might have a sewage treatment plant, and they're taking some of their off gas and they're running a generator to supply some of their power as well. And
Gotcha.
those would be AC generators.
Gotcha. All right. So,
Uh, a lot of times chemical plants too, they'll have steam loads and they'll use a steam generator, and these can be big ones too, running a generator in parallel. So
yep. And you threw the loads in there because is that a distinction of a microgrid? Do we have to have the loads in there?
well, yeah, you do. Here's the thing, and I'd say this is an example microgrid where you have the grid and you have a microgrid interconnect device, and you have any number of PV, wind generators, maybe energy storage systems, and loads. If you just wanted to be a generator, you would probably be just a commercial generator, and probably the small ones don't make a whole lot of economic sense.
Right.
But when you're supplying some of your load, remember, with the utility price on their energy, you've got not only the energy price, but you also have the price of the line trucks and the infrastructure and everything else. So that the energy side of it is one component, and the other side is the utilities infrastructure and margin and that kind of stuff. It's kind of like going back to your example of your grocery store. I might buy tomatoes for 50 cents a piece,
Yep.
and I sell them for $1 a piece, and the difference between is my infrastructure and my profit and everything else. And when you want to come in and supply tomatoes to me, I'm only going to pay for your 50 cents worth of, because that's what I buy them for.
Right.
But if you supply tomatoes to yourself, instead of buying them for me, it's worth $1.
Yeah.
$1 tomato. So
I never thought about it that way. So that explains. So I bet you there are some people that get shell shocked when they think they're going to sell back to the utility energy, and they realize, well, they're not giving me as much. I'm paying more for it, but they're not paying as much. But they're forgetting about that whole infrastructure concept.
yeah, and the infrastructure and the other things. So that say you buy, we'll just give you an example, 10 cents per kilowatt hour. Okay.
Right.
So you're buying electricity for 10 cents a kilowatt hour. When you generate it yourself, you're generating for any of your own loads at 10 cents a kilowatt hour. But if you're going to sell back to the utility may only give you 6, 7 cents or 5 cents a kilowatt hour. I don't know what the numbers would be,
Yeah.
Because that's essentially what it takes for them, and everything else is the business side of the service that they sell.
That's right. Yeah. That is really interesting. I never thought about it that way. Now, this discussion here is speaking to what I think it was Robert from Omaha was talking about, protection of this equipment. So you're tying into the utility. So there's your meters. That's your service, right? So you have your service over current protect device. Or now that disconnect, this disconnect right. I'll put my laser pointer on. This disconnect right here. You're saying that's the microgrid interconnect device?
Yeah, now that's the device that will allow the interconnection with the utility or allow the microgrid itself to isolate. And this is just one example. This is one of the things that Article 705 is, when I go through a couple of slides, some of the concepts that Article 705 is trying to, prevent from happening. Okay.
Right.
So we'll see some requirements when you connect your distributed generation at some other point other than the service, or right at the service, or right, ahead of the main disconnecting means.
Now, would that mid have to be service entrance rated because it is connecting to the utility?
Oh, certainly it would be, because you're between the meter socket and the main disconnecting means. It certainly would be service rated. It would be like a service rated automatic transfer switch.
Gotcha. Now, I could, if I wanted to, I could make a.
I forget what the UL number is, but yeah, well, suitable for use of service equipment or service rate. Yeah.
Now, if I wanted to integrate that with my panel board, I could do that too. If I wanted to get innovative and say, hey, I want to make a panel board that's a mid, like an inverter would be, I could possibly put the technology right in the panel board.
Absolutely.
That's interesting. Okay.
Yeah. So here's one of the issues, and this is the panel board overload protection that Article 705 deals with. Here we have the panel board that you see has the single main, and the power flows from the utility down through the main breaker into the panel board. But you'll have also feeds into the main panel board from your generator, from your PV, and from your wind system into your panel board. And right now we're feeding back out to charge our energy storage system, and we're feeding our critical loads. Because power is flowing in multiple directions, not only through the main overcurrent devices, but from those branch feeder breakers into that, it's possible to overload your panel board. So that, when we talk about 705.13, there's requirements for how much generation that you can put into the panel board so that you don't overload the internal components of the panel board.
That's right. Yeah, 705.13 talks about a power control system.
Correct.
And it says a power control system shall be listed and evaluated to control the output. So this is not the mid. So Robert from Omaha's perspective, he was saying, does the mid do that? But that's not that's not what it is, right?
No, that's not what it is. Now I gave you the wrong reference. It's 705.12.
Okay.
705.12 is the load side.
Connection. Yeah, that's your load side source connection. So that's what this is. When we say load side, we are load side of the main overcurrent protective device. So all of this is on the load side of the main service disconnect, and now your mids up here, and now you're more worried about this bus infrastructure of this equipment because of the current flow in the system.
That's correct.
Boy, see, I'm teachable, aren't I? I'm learnable. I can learn.
Oh, hey, you're picking up really well. I mean, that's the issue of 705.12. Truthfully, it's not a utility issue,
right.
But it is, when you have multiple sources, the premises wiring system is originally designed to be a radial system, source to load. When you have other sources in different places, then you've got to worry about, your overload protection. You got to worry about your short circuit and overcurrent protection as well. So I'll talk about that in some other slides, but this is the 705.12 issue.
And that bus that's feeding the loads is rated, say, for so many amps. Say it's 200 amps. And typically, since power is always flowing from the utility, that main overcurrent device, which would be 200 amps, would protect the bus. But now I can pull 200 amps from the utility. I could have 100 amps coming from the generator. I could have 100 amps coming from the wind and another 50 coming from the PV. And then I could add more loads in that panel board and overload the panel board because I've got multiple sources now. That's what you're getting to.
That's correct.
That makes sense.
Yeah, I don't have anything on 70513, which we could talk about a little bit later, but that's a 70512 issue. The other thing comes in is panel board short circuit protection. In that, most utilities for 1 and 2 family dwellings limit the amount of short circuit current to under 10 kA. And the reason why they do that is so that you can use residential class panel boards and residential class equipment, which is generally 10 kA rated and below in those applications. Now, when you get into a commercial or business application, industrial, something like that, then you're going to have a lot more short circuit current than 10 kA. You might have 65 kA or something like that, or even higher. But in a residential issue here, this is the thing where you might have something like a larger transformer, and you have up to about 9.6 kA from the utility available, which is well within the interrupting rating of that main circuit breaker. But you have energy storage, you have generator, wind, PV, and that type of thing also feeding into it. And say you have a downstream fault on one of your breakers, that feeder breaker or branch circuit breaker could be over duty because the utility is going to put in about 9.6 kA, and the other
The
ERs,
generator.
yeah, they can put in additional, and you might over duty that breaker. So it's an issue to deal with on panel board short circuit protection, or at least it's the overcurrent device short circuit protection could be over dutied on that.
Yeah, and in reality, it would be a short circuit current rating issue, but in a panel board, we determine the short circuit current rating based upon the lowest interrupting rating of any single device.
Right.
Yep. Logan had a question again. Logan Millington on YouTube. Energy storage. No, wait. Can you please explain the functionality differences between a mid and a multi-mode inverter?
Okay.
If he wants to install a system that is a PV array and utility, but with the option to expand to energy storage, should a mid be installed for future use or just a multi-mode inverter?
Just a multi. If you have a multi-mode inverter, essentially you have a utility connection to the multi-mode inverter. You have AC or DC from your supplies into your multi-mode inverter, and the multi-mode inverter is supplying power to your loads. Okay.
Right.
So that multi-mode inverter is acting like an automatic transfer switch, if you will. Okay. You may have some energy conversion that's going on in it from DC to AC, but essentially you've got a utility side connection, you have distributed resource connection, and then you have a load connection. Now with the mid, the mid itself, and that would be a mid, a microgrid interconnect device, because the multi-mode inverter can supply power from your DC side to your AC side on your critical loads, or it can supply power back into the utility, interconnect the utility system. So it's actually functional as a mid. The other thing is, I show here is a mid as a switch device, okay, in that you have some type of detection on that microgrid interconnect device, and then you have AC couplings between all your generation sources and all your loads.
Yeah. So in essence, for Logan's application, if I was Logan, I would probably go to whoever my inverter manufacturer that I select. I would say, look, I want a multi-mode inverter that's listed as a mid as well.
Yes.
And then you've got it. So for the future, you've got it. For the present, if you don't need it, then you don't have to worry about it. But at least the capability is there. And that just means that it's following the rules to play good with the utility.
Right.
I like it.
And that's what the utility industry is mostly concerned with.
Yeah. So you're just and I think we had a discussion. I think it was last year. It might have been this year. I think it was last year. You had made the statement that we're relying on that certain things to behave in a certain way. So you create the standards, and then you got to make sure that the installation requirements are married with that to say, okay, I got this beautiful standard over here, and it says that this product has to behave this way, but we need something in the code that says you got to install that, and it has to be listed to that standard that you spent all those years on. Now, you were involved with the creation of 705, weren't you?
Actually, no.
Okay.
was created, let's see, by Panel 15, when, I don't know if you remember Ed Laurie, when he was chair of that.
Yep.
And they were talking about at that time, paralleling of generation and also interconnection of utilities. And mostly up until, I don't know, maybe 5 cycles ago, before EPAC 2005, it really wasn't much of an issue. You had the Public Utility Policy Act, but you really didn't have very many distribution interconnections prior to that.
Right.
After 2005, the utility industry got very interested in Article 705 to make sure that, all the standards and all the equipment and everything played well together.
Gotcha. Now, this one shows when you have a fault on the utility side. So you guys screwed up. And now
Yeah.
I got to consider that, because now I've got fault current that's coming from my facility because I've got generations and wind, and now I'm going to be putting that back on to the utility.
Yeah, probably this is a concern to think about. Say, like, a tree falls across your service entrance or something like that, or you have somebody digs into your service or something like that, and you have a short circuit on the service side. You're going to have to rely on that all that distributed resources to trip offline, or you're going to be feeding fault into an upstream fault. Most likely, you're not going to over duty those devices, because most distributed generation isn't going to be outputting, like 5 or 6 times its normal running current. It's probably 1.2, 1.1, 0.3% of its 1.1 unit of its equipment, except for that generator. That generator might put out some significant fault current.
Yeah.
So from a fault current standpoint, it's not really an issue. But again, you've got to come offline so you don't feed fault current into an upstream device. So you're looking at not only downstream overcurrent protection, but you're also looking at upstream overcurrent protection as well.
And there is also a concern from a worker safety perspective. If you are up on the pole and you've established I'm disconnecting the lines, but the homes are still connected, if they're putting power up onto that, you could have a whole separate little island going on where they're trying to supply power to each other because they're putting power back up on. But those inverters have to behave correctly, because whenever they lose power, aren't they supposed to shut down?
Yes. Yeah, they're supposed to cease whenever you have that they're not to create an island outside of the premises wiring. So that's that anti-islanding protection.
Yeah.
A microgrid creates an intentional island. The other protection prevents an unintentional island from being created.
And so anytime, if I am going to be operating, if I'm going to put my distributed system on and operate in parallel with the utility, do I have to contact the utility, or do I just make sure I have the right parts and the inspector make sure that they're listed correctly? Am I supposed to?
There would be an application process, a contact of the utility when any type of alternative generation comes online. It's just to make sure some of those issues we talked about before with voltage balance and other things are properly designed in.
Excellent. Okay.
The other thing that I want to talk about from a safety aspect, 70520 always talks about the source disconnecting means. Realize the utility follows the same regulations for OSHA. It's a different requirements. It's not in the 1910 300 through 399 sections. It's 1910 269, but it requires the isolation of all sources of energy. So that disconnecting means has to be readily accessible. And when you look at the term readily accessible as defined in the code, it's by those who need to be able to access that disconnecting means.
Right.
So utilities standpoint, they may need to isolate that. Now, sometimes it can be done with a meter socket and meter, but other times, say they're working on the meter socket, they need to be able to isolate any source coming into the area in which they're working. Same as we have the same lockout and tagout requirements that everybody else does too.
That's right.
So, just to let you know about that disconnecting means. So
yeah. So let's talk about that real quick here. The in like Article 690 has a PV disconnect requirement, right? I can't remember the numbers off the top of my head. You got 690. You got
694.
Yep, 694 for wind has a disconnect requirement. So an energy storage system has a disconnect requirement. So all of these systems have a disconnect requirement. And what
Right.
you're telling me is if I have all of these systems, they all have disconnect requirements, and I'm going to connect in with the grid, I'm going to be following 705, which tells me I need to have them readily accessible, and I need to have them. Do they all have to be next to each other?
If the Article 70520 gives you that requirements for that source disconnecting means. Now, you have disconnecting means for the premises wiring system that you'll see in 690, 694, and other places.
Right.
But the one in 70520 deals with the one the utility has to deal with.
Ah. Okay, so and it says located. So it says means shall be provided to disconnect power source output circuit conductors of electric power production. So I could, if I have like this one here, I have a generator, wind, and PV.
Right.
I would have 3 disconnects.
Well, actually, that main on that one can supply as that disconnecting means.
Oh yeah. But yeah, you're right. But if I had an inverter in there and it was going and it was on the line side of this main service disconnect.
Right.
So if I had the generator, wind, and PV connected on the line side, so that would be connected. So if this came up like this.
Right. If that was connected to the line side, that disconnecting means would have to be readily accessible for the utility industry as well.
And I'd have 3 disconnects, right?
Right.
Yep. And then Robert from Omaha points out labeling is really critical, but because you need to know, I mean, when your utility guy comes over, he needs to know there is generation local in that
Right.
location.
Right. And, the identification of the power supply sources in 70510 is there. And, you have all this kind of, these requirements that you see in 705.
Yes. All right. I got to catch up on some of these questions. You got to love the firmware. Yes, they're supposed to shut down. Oof, when they do not shut down. Unless you have AC or DC coupled systems, means you can touch it. I'm not sure where that was going. 690.13 PV system disconnect. Yeah, so Robert was pointing out that there's a 690.13, and then Ronald Ramirez on YouTube was talking about NFPA 110 covers generators. And now it's going to be starting to cover energy. What do they call it?
Article 855 is now a new article or a new standard for the NFPA.
That's right.
And that covers energy storage systems. And
Yep, absolutely.
Have those requirements. And the big issue with those energy storage systems is we're no longer dealing with lead acid type of batteries. We're dealing with lithium ion technology that can run away. And if you were at the annual meeting, the last annual meeting with We Could Meet Face to Face, there was a lot of people talked about when these things go, they really go. And even the fire suppression equipment can't shut it down. They've sprayed water on them and they still continue to go with these lithium based systems. So, that's a whole unique area. When we start getting lithium-based technologies that you find in your cell phones, in your electric vehicles, and your energy storage systems, the fire protection requirements have to come out, and a lot of that deals in Article 855, or excuse me, NEC Standard 855. They're pushing all these requirements because you're generally looking at a lot of energy storage providing backup power, mostly for photovoltaics when the sun doesn't shine.
Yeah, absolutely. Okay, so
this is a great area to work in. I have tremendously enjoyed it.
You gotta love it. Now 710 has been a controversial for a lot of reasons with regard to inspectors on trying to understand when does 710 apply. And because you got 710 and you have another one. There's a 7. What is it? 710 and is it 7? That was 712. Yeah, your microgrid. Well, that's direct current.
That's DC microgrids.
Oh,
yeah.
no. It was the difference between 710 and a 702, with a transfer switch, the optional standby system. So I have a generator and I have a transfer switch, and my transfer switch transfers, and now I have a generator supplying a house, and it's standalone. Is that a 702 or is that a 710?
Well, if you have a transfer switch, okay, and there's no interconnection, all right, it's a 702 connection. Okay. Now, a standalone system has no utility connection at all to it. It basically is, photovoltaic cells or whatever, generation source and load. There is no utility connection. I have some pictures here of, like a speed monitoring sign, or, living off the grid,
Right.
parking meter, a remote weather station, those types of things. Standalone system has no utility connection at all. Utility connections where there's an automatic transfer switch and there is no paralleling of the generation except for maybe a momentary make before break. The transfer switches may permit up to 100 millisecond paralleling.
Yep.
Utility industry really doesn't get concerned with that because the generation is not in parallel for very long. And the only thing they really worry about is during testing, say that, when you test your generator, your standby generator, or your legally required standby system, that whenever you come back and you dump the load back on the utility system after testing, that can cause a voltage anomaly.
Yeah.
That's really the only time that they get concerned with it, is how much load you dump on the utility system at one time, because it affects voltage regulation. Other than that, if it is an interconnection, utility doesn't really care.
Yeah.
So automatic transfer switches are not an issue. Standalone systems are not an issue. It's the interconnected ones that cause for at least additional care and feeding with those systems.
Yeah. The only issue you got to worry about here from an application is, do you have enough solar to power the load, and for how long? And do you need some batteries there? I would love to see those radar detectors just shut off in the evening and turn on in the morning when the sun came out, but then they put those batteries things on there.
Well, something that the correlating committee, am I online? There we go.
Yeah, there you go.
Okay. Something that the correlating committee has to deal with, you have energy management systems in Article 750. You have power control systems in 705.13, and you're going to have electric vehicle load management systems in Article 625.
Right.
All of those things in the new world are going to have to interact and work together, because if you don't have enough generation, you're not going to be able to supply any load. So you might have to load shed. There's requirements for hospitals and healthcare. You can't shed the elevator load, that kind of stuff, for legally required standby systems. So, you either have to have as much generation available as your load, or you have to shed load or be able to determine how to control that load, in order for your premises wiring system to work correctly.
Yeah.
And we're going to see more of that coming out with those three technologies: electric vehicles, interconnected generation 705, energy management systems in 750. And I know from panel 12, we recommended to the correlating committee that a task group get together. I've not seen that that's been done yet. We recommended to the correlating committee that, these different panels come together and say, hey, you got panel 12, you got panel 4, and you got panel 13, come together and, hey, how are you guys going to work on this?
Yeah, absolutely. Would there be some good resources for guidance on how to suppress lithium-ion battery fires? Yeah, well, I'll try to do is reach out to NFPA on that one.
Yeah, there was, during the annual meeting, there was quite a bit of discussion in the testing that was done, and even the different types of lithium-ion technology. One is better than the other. But yeah, those are.
Yeah, absolutely.
The NFPA 855 committee would be a great source for that.
Yep. Santiago made a couple comments. Oh, so he's asking about the safety, and he made a comment up above. Let me just go up and find his. I don't think I can search the chats, but he says at some point it would be feasible to see or bring someone to speak about the hazards of distributed resources. What would be the hazards in a community center, in a rural area, or similar site? And I think that might be related to his other question here, was where he's saying, Um, uh, where's it at? Right here. Would there be any special considerations for remote areas to verify safety? So Santiago's got his safety hat on, and I think there's the aspect I think there's two things. There's the safety with regard to shock and arc flash and all this other good stuff, right? All your electrical hazards. The other safety aspect is, what are you using this to power? And I know that 110 and 111 and Article 517 and NFPA 99 are starting to recognize what is, and I can never remember the technology. It's a hydrogen based power generation. It's like a generator. I can't think of the name. And these guys will bring it because I had the same brain issue one time, and I know Randy or Logan or Ryan, one of these guys will remember. It's a hydrogen based generator, so to speak. We're recognizing those in 110, 111, NFPA 99. We're not recognizing the energy storage system as a valid supply, nor photovoltaics, because the argument there is, when the wind goes away, you can't rely on it, right? And even if you had the batteries and how they work together, fuel cell. That's what. Thank you, Ryan. I knew you would remember.
There you go. Okay.
So a fuel cell is not an energy storage, and I know this is a debate. There are some people who will say a fuel cell is an energy storage system, and it's not. It's a generator, in my opinion, because
Yeah, it's an energy converter. It converts, you frack natural gas into, the hydrogen components. It's a hydrogen and oxygen fuel cell.
right,
You either got a polymer electrolyte, or you've got molten carbonate, or you've got some other, electrolyte, and you're feeding it fuel, which is hydrogen and air or oxygen, and you're generating DC out of it, and then you would invert that back into, some type of AC power. So it's not really energy storage because, it requires, natural gas to power it,
right.
but it could be used as a, smoothing source.
Yeah. So they're recognizing. So and we lost Amy Nelson. Thanks, Amy, for joining us. She had to drop off. Santiago. So I would say, from a safety perspective, you have the shock and the arc flash, which we're addressing, right? We're doing some more DC testing. We're going to come out with equations on IEEE 1584. We just did some testing down in St. Louis a couple weeks ago, over the last few weeks. So we're trying to build out those equations to help you understand the arc flash from a DC perspective. There are ways to calculate that. From a shock perspective, you've got the rapid shutdown requirements for the first responders, all that good stuff. But from the other aspect of safety, and I know you talk about remote environments, but you got to understand, what are you using for? And if you're relying on that for a safety process, you've got to understand, am I using the right technologies to get that done? So,
Right.
And I'd go back to 110, 111, and other standards that exist from a life safety perspective. They'll tell you, you can't use this, but you can use that. And there's some prescriptions that, like in Article 700, and for like fire pumps and things like that, they'll tell you what is a reliable source, and they'll give you that guidance. So check the fire pump code requirements, Article 700, 701, 708. And I think you'll get into that in FPA 99, et cetera. All right. So when I look at everything that we talked about, we went over the codes and standards. We talked about the IEEE standards, the UL standards, and NEC articles. We dug into those. Talked a little bit about deregulation. What's EPEC and how utilities have changed to accommodate you. We talked a little bit about that.
Yeah, the EPAC 2005, that was the Energy Policy Act of 2005, went out to the state regulators and said, hey, you guys got to figure out a way to connect this alternative generation, the solar, the
wind.
just yes, not only solar and wind, but also like waste heat and other renewable sources. That's the term I was looking for. Other renewable sources to interconnect those. So that's what EPAC 2005. They went out to each state. Each state adopted generally IEEE 1547. Most states adopt the National Electrical Code, as they adopt the National Electrical Safety Code as well for the utility industry, or some version of that. Like in California, they adopt their own version of both of those documents and, go forward. So EPAC 2005 is really what brought a lot of this stuff in and what, allowed these interconnections to occur, and also, kind of kick the utility industry in the pants to saying, okay, you're going to do this, so you got to learn how to do it safely.
Okay, crack the whip on you.
Yep.
Yeah, and we talked about the interdependencies. We talked about the secondary network versus spot network versus regular distribution. I know we talked a little bit about that, but I'm not sure if I don't know if that really matters, to tell you the truth. I mean,
the only thing in a low voltage secondary network, either it's the the complete secondary network or a spot network, whenever you have more generation than the load is on that system, you can cause the network protectors to operate. And, you lose the network protectors, you'll lose the utility source. It's like a backfeed. They're not designed to backfeed. And when that backfeed basically on the transmission system that's supplying that network, you lose the network.
okay. Yep. So I think we hit all of the topics that we set out to talk about. So we talked about all the different connections and line side connection, load side connection, the mid. We know what the difference between a mid and inverters and all that good stuff and how they can work together. We know what the utility cares about. It's frequency, it's VARs, putting VARs onto the system, impacting voltage. What did we miss, Tim?
I think we covered just about everything. There's one thing that I did want to talk about,
Yeah.
and these were the types of electric utilities.
Oh, yes.
Yeah. So, generally utilities are classified by who owns them. Okay.
Uh-huh.
And you can have federally owned utilities, electric utilities. And just give you an example, like Bonneville Power Administration, Tennessee Valley Authority, the Hoover Dam. These are all federally owned utilities. And most of those federally owned systems are dealing with transmission and generation. Okay. But when we deal with IEEE 1547, we're dealing with distribution types of utilities. And there's a few different types of those. One is you have municipal owned utility systems. So like you might have municipal water, municipal sewage, you have municipal electric utilities as well. The city of Austin, Texas is probably one of the largest municipal systems, but they're generally a city or a community type basis utility system. And they take power from the bulk power system and they distribute it out. So anytime you have to apply to these interconnections, you're applying to these individual entities that supply power to its customers. So you have the municipal owned electric utilities. Those are generally, there's an organization, American Public Power Association or APPA, that looks at the municipals. Then you have the rural electric or the co-op owned electric systems. Yeah. And those are, they usually fall under the National Rural Electric Co-op Association or NRECA. Okay. And they're mostly distribution utilities. Again, they're looking to distribute power, and you would be, communicating with one of those co-ops whenever you had an interconnection that you needed to have.
Right.
Then there's investor-owned utilities, and I worked for an investor-owned utility. I finished at First Energy, but these are ones where you have, shareholders. They're commonly the shares are traded. If you look at most public service, public utility associations or systems, they're said to private ownership, but they're generally owned by investors or stock ownership. So those are the three major ones. Probably about 2/3 of the power in the United States is supplied by investor-owned utilities, and the rest are rural electric and municipally owned. However, you do have a few privately owned electric utilities, and we have maybe a small group of investors, like Duquesne Light, for instance, is privately owned by a small group of investors.
I did not know that.
Just to give you an idea. So, they fall under this investor owned, but it's a small private group that owns, like Duquesne Light. And I haven't looked very much, but there used to be a few still mom and pop owned electric utilities. There used to be one in West Virginia. I believe it was Elk Power Company, and they were in like Clay, West Virginia. And they had like 5 or 9 employees, but they were a small little mom and pop distribution utility. I can't tell you if they're still in business or not. I got some, when I looked, I got some conflicting information on Google when I started searching them. They still have a business association, but they're no longer listed by the West Virginia Public Service Commission as a utility. So I don't know if they're still around.
And that could be why it's in some cases. I know when I would do short circuit studies, sometimes it would be difficult for me to get like available fault current data from a utility, but it could be because they're a very small co-op and they don't have those resources that say a public utility or even a large co-op might have more resources than the smaller individuals and privately owned or whatever.
Yeah, and that's kind of the misnomer that we see is that word public utility. And sometimes they are publicly owned, like the co-ops or
Right.
the municipals, but sometimes they're investor owned, so that they're owned by shareholders and stockholders and things like that. So even though that the company that I work for, First Energy, was a public utility, it was owned by private investors, so shareholders and things like that. So it sometimes what we call things isn't necessarily what they are.
Right, right.
Yeah.
Yeah.
But depending on the size of the utility, you may or may not be able to get the types of information that you need to do your studies.
Yeah, and they may require they may have different requirements placed on you with regard to what you can maybe put on the system or not put on the system.
Right. Depending on the size and the strength of their system that you're going on too.
Okay, so back to that other picture that you had about, like, remember we were talking Hawaii, right? And they're small. And we were talking about the northwest, northeast grids and all this other good stuff. In those big areas in that map, you'll have multiple generating stations that could be privately owned. It could be owned by investors. It could be owned by the government, right? Like in the case of Hoover Dam. But each of those little systems, those are still interconnected. But you're saying they're even small on their own because they have their own distribution.
Well, the distribution system is not interconnected, but the transmission and subtransmission system generally is interconnected. Now, you can have radial transmission or radial subtransmission. That's possible. But the distribution system generally comes from a substation out through circuits, distribution feeders to serve the load. And those are generally not interconnected.
Ah, I did not know that. Okay. That's interesting. That's interesting. And look, a LinkedIn user said that is an interesting point. Now, I have to say, Ryan had a question. What do you know, and what can you tell us about those meter-mounted transfer switches? Why do utilities like them or don't like them? Do they like them? Do they not like them? What's going on with that?
Well, that's the big question. And if we could get a good answer between all of us in the utility industry, you're right. Some like them, some don't, and
yeah.
A lot of it depends on where the service point comes in at too, is, the service point, which is a defined term in both the National Electrical Code and the National Electrical Safety Code. It's where the, facilities of the utility stop and the premises wiring start. Sometimes that is, the secondary terminals of the meter socket where the service point is. And sometimes that's, the connection on an overhead service at the weatherhead. So, where that service point is depends on, whose jurisdiction that piece of equipment may go in. And, we've had lots of spirited debate in our utility, discussions about those meter mounted transfer switches. So some people like them, some people don't. And it's
a plot shot. But to your point, with all those different systems and whether they're utility or whoever the owner are, and how they're configured, they'll all have different opinions. So you may come to one jurisdiction that says, yeah, we'll let you put them in. Another one says no. But what was interesting was somebody had asked me a question about a meter center or a meter stack or whatever. And they say, can you get me the information on it? So I went on our website and I searched on meter centers. And then I got a whole like 5-6 different pages, and it was like, here's a meter center for Pennsylvania Power and Light, here's a meter center for Duke, here's a meter center for Georgia Power, here's a meter center for AEP. I'm like, oh my gosh, all these different utilities have different requirements for that meter stack or the meter center. I mean, and we actually build them differently for them. I was just amazed at how many different The product lines, our product lines, and I'm sure every manufacturer product line's got to go nuts when you have that one utility go, we don't like the space in between here and here. We want it to be wider. Oh,
Yeah, we need a barrier here, or we need. Yeah, I understand.
yeah, unbelievable. Make sure. Yeah, okay. Robert from Omaha. I never say this, Tim. I got to tell everybody to hit the like button, hit the thumbs button. I love the dialogue that's going on. We're getting a lot of good dialogue from LinkedIn and YouTube and Facebook. So it is beer 30. It is true. What else? Do you have something else you want to cover, Tim?
I think we hit everything that we talked about previously, and just one anecdote I will say.
Yeah.
You didn't know what the NEC Quarter Century Club was.
What is that? Yeah, what is that?
When you have been on one of the code making panels or the code making panels for more than 25 years, you get officially inducted to the NEC Quarter Century Club at the annual meeting, and you get a nifty little pin.
Oh, look at that. Wait, no, hold on. Yeah, there it is. That is cool.
So I've got 30 years now in, a little bit more than 30 years in the NEC. And, you get a nifty little pin. And if you're really good, you get a nifty little NEC tie.
Oh, look at you, man. See, that's hilarious. That is awesome. Man, 25 years. God bless you, bro. Wow.
Yeah, it's an annual ceremony. Every time the code is voted in at the
annual meeting.
The annual meeting, the electrical section meeting, the annual meeting, you get the 25-year members get get recognized into the Quarter Century Club.
Wow, the Quarter Century Club. That and what, $1.50 will get you a beer?
Something like that. Maybe maybe more like $5 to get you a beer.
Yeah, that's the truth. That's the truth. Awesome. All right, Felix Sandoval, thank you for the feedback, brother. Robert from Omaha, thank you as well. And everybody else out there, do these all fall under utility regulatory commissions? Utility regulatory commissions. What's wait, we talked about that, right? Didn't we?
Yeah, usually, the public service, public utility commissions, and they generally look at the distribution type of interconnections. Yeah, they generally regulate the distribution system. Mm-hmm.
All right. Oh, and Tamaki Ono is out of Japan. Thank you for joining us. It's the symbol. That's right. So the symbol that was on your tie was the symbol that's on the code book. That's exactly right. So that's kind of cool. And we've received over 100 messages. Thanks for all the questions. So my Restream IO is telling us we had a great dialogue in this session. So thank you. And Tim, thank you for joining us. Kevin Breen, Mather Abbasi, another panel 2 member. Hey, Mather, we gotta educate this guy on panel 2. So we gotta watch, him, gotta keep him, gotta keep him under wraps. So Mather Abbasi, thanks for joining in as well, and Kevin and crew. So thank you, Tim. I really appreciate it. You gave 2 hours of your time tonight.
Thank you for having me, Tom. I really appreciate it. It's been my true pleasure to talk with you.
I appreciate it. Excellent. And I know everybody out there is thanking you as well. So everybody, thanks for a great evening. Thanks for hanging in there and asking all the questions. So remember, we're going to sign off now. Remember to please stay safe and stay healthy. So until I won't be here Thursday. I'm going to be down in Dallas. So next week, we're going to have a good program for next week. So Steve Froming, still out there. Thank you. Thank you, Tamaki and Mather and everybody. All right, signing off for the day, for the evening. Everybody out there, take care. Stay safe.